So I'm going to sort of swiftly get into this session because, as I said, we've got a packed agenda. So my name's Dave Lowe, and I'm the Senior Director of R&D at One Lambda. And I'm just going to set the scene for what I hope is going to be a very stimulating and engaging symposium over the next hour and a bit. So I'm not going to dwell too long about this, but the real focus of today's symposium is around epitopes. We've got two really nice presentations. Oh, three actually. Sorry, Bob, I forgot your... Three and a quarter. I'm not giving you half. We got 3 1/4 presentations. No, it's 2 1/4. Oh, Bob. We've got 2 and a bit presentations for you today, so we better get on with it. But it's all around epitopes, and I'm not going to dwell too long on this because I know this is familiar, and these concepts will be covered in great detail by our presenters. We're going to sort of elaborate on some of the commonly used phrases when we talk about epitopes, eplets, and so on. I know it's something that often we get a little bit confused over, but I'm sure everything is becoming a lot more clear, certainly over the next hour. I just thought about this when preparing for this sort of presentation, about sort of from my time in this. So when I started in the HLA lab in Birmingham in the UK, way back in the 90s, that was the first thing they got me to do, was antibody identification, which meant that I spent about 4 weeks doing CDCs just to get one result. And we got a lot of tools today, but I remember back at the time, these were my tools for antibody characterization. There's a few nodding heads. So they basically gave me a job straight out of university where I spent most of the day coloring in. But there were a lot of fun those days. And then we sort of progressed and we started to make our own grids and tables. And now we've got some great tools. So obviously there's many of these are very familiar. We've got Matchmaker, HLA-Emma, we've got the sort of devisers of that taking part in this symposium today. And many of us will use the epitope registry, and I know there's a big initiative to sort of revamp that and standardize that, which we're going to be really pleased to be able to support over the next few years. And even from our side, we're always looking to build in more functionality, more ways that you can study epitopes and elucidate some of these patterns. So, coming up in the next few months is going to be an update to HLA Fusion, for example, where we've built in a lot more epitope functionality. So I'll finish there because I guess we're already behind schedule, but I'd really like to introduce our moderator for today's session. And it's someone who needs no introduction to those of us in the room, so I won't give him one, but I'd like to welcome Dr. Bob Bray up to the stage to moderate today's session.
All right, thank you all for coming, and welcome to everybody. I won't talk a whole lot up here, but we'll get started. Our first presenter this morning, or this afternoon, is Suzanne Bestarosti. Suzanne studied medicine in Leiden and is currently doing a PhD in transplant immunology in the Department of Immunology under the supervision of Sebastian Haidt, who's going to join us a little bit later for our roundtable discussion. Her research is going to focus on, oddly enough, HLA immunogenicity and clinical application of eplets. At the end of this year, she'll complete her PhD and start a role as a clinician in internal medicine. So without further ado, Suzanne, come on up and let's get the ball rolling.
Yes, thank you for the introduction. And I'm very happy to be here to present our work, our collaboration of our Leiden group with One Lambda. So I'll be talking about site-directed mutagenesis of HLA molecules as a new approach for HLA eplet verification. I have no conflicts of interest to disclose. So here, a very familiar slide probably to you all, that HLA matching in kidney transplantation is still very important despite powerful immunosuppressive drugs we have nowadays. So every HLA antigen mismatch actually leads to an increased risk of graft failure. And this is due to the formation of donor-specific antibodies directed against this HLA mismatched antigen. So these antibodies, these HLA-specific antibodies, are induced by mismatched HLA eplets. So just first a brief introduction of HLA eplets. These are theoretically defined small patches of surface-exposed amino acids on HLA molecules. And the definition describes that they are within 3.5 angstrom radius. So here we see an example of one of the eplets on an HLA-B molecule, where you see the HLA molecule from the top. So the peptide in the peptide binding groove you see in gray. And you see here 3 amino acids that together form this eplet. So these eplets determine the antibody specificity through interaction with the CDRH3 region of the antibody. And several studies have demonstrated an association between eplet mismatch load and the formation of DSA and graft loss. But these eplets have been theoretically defined based on the amino acids, the differences of the amino acid sequences of all these different HLA alleles. And therefore, we need antibody verification to really validate the fact that these eplets can be bound by donor-specific, by HLA-specific antibodies. So we do that with antibody verification. And also studies have shown that indeed these antibody-verified eplets, so this subset of eplets, are associated with graft loss. So for instance, this is a study in a North American cohort of more than 100,000 renal transplant recipients, where it was shown that for each eplet mismatch, there was an increased hazard ratio for graft failure in these patients. But also in a cohort from Belgium in Europe, we see that antibody-verified HLA-DQ eplet mismatches were associated with inferior transplant outcomes. So there was a higher risk for DSA formation, graft rejection, and also graft failure. So therefore, we do need this antibody verification to validate really the clinically relevant eplets so that we can, in the end, use these eplets in a transplantation setting. And human HLA-specific antibodies are an excellent tool to do that. So there are multiple ways for antibody verification that have been described in the HLA epitope registry. And human HLA-specific monoclonal antibodies, well, we think that that's really the best method to do it. And here we have an example of, for instance, an HLA-A3 specific monoclonal antibody that verifies the eplet 161D. So here we have the monoclonal, and we have tested this monoclonal in a single antigen bead assay. And we see here that it's really one bead, one allele that's positive, and that all the self alleles and also all the other alleles in the panel are negative. And if we then look at the amino acid sequence, we actually see that the position 161D is really the only amino acid that is present on the A3 allele, which is not present on any of the other negative alleles. So what we do then is actually look at the position of this amino acid on the molecule. So again, here we look at the top of the HLA molecule to see where this eplet is located. So this is a very nice method which we have used for quite a lot of HLA-specific antibodies that have been created in the lab in Leiden for the past years. But sometimes the analysis is not so straightforward as here. So sometimes we do not find only one amino acid that is shared by these reactive alleles. And this is an example of such a monoclonal antibody. So here we see a pattern of a HLA-A1 specific monoclonal antibody. And here we have 2 beads that are positive, and the rest of all the beads in the panel are negative. And if we then look at the amino acid sequence of the differences and the similarities between all the different alleles in the panel, we identify 3 positions that are uniquely shared for these 2 alleles. So in this case, it's position 44K, 150V, and 158V. And if we then look at these 3 positions on the HLA-A1 molecule, you see that they are quite far away from each other. As you might remember, when I introduced eplets, the definition is that they have to be within this 3.5 angstrom radius to be able to bind to that single CDRH3 region of the antibody. So if we look at the distances between these amino acids, it's actually way more than these 3.5 angstroms. So here we can safely say that it's not possible that these 3 amino acids together are really part of this same eplet or the same functional epitope. So we've called this this pattern a reactivity pattern, because we see this pattern in a single antigen bead assay, but we cannot really pinpoint the eplet that is really recognized. And so therefore we thought that the strategy to really resolve this is for site-specific single amino acid mutations on the HLA molecule. Because we, of course, looked first if there were any alleles maybe that were not in the panel, but maybe a bit rarer alleles which have only a 44K, for instance, and then different residues on positions 150 and 158, but they're not there, they don't exist. So therefore we really need mutagenesis to create these type of configurations. So what I first want to do is show you the analysis that we've done for this specific HLA-A1 monoclonal antibody. So here we see the whole single antigen beat data of this monoclonal antibody. So we see the two, so the A1 and the A36 allele that are positive. There were also some alleles that have a bit lower reactivity in the single antigen beat assay, and we thought that this was not really a really positive outcome. So therefore we also looked into the CDC scores to see if there was really binding of the antibody on a cellular level, and then we see that really the A1 and A36 are also positive in the CDC assay. So we considered really these two alleles positive for this monoclonal antibody, and then looked, okay, which of these three potential amino acid residues would really be crucial for the antibody binding to the HLA-A1 molecule. So that's a question which we try to solve with this strategy. So therefore we seek the collaboration with One Lambda, and we made single amino acid mutations of the HLA-A1 molecule. So what we did is actually mutated the amino acid residue of interest to the self residue of the antibody producer. So the 44K residue was mutated to an R and also to an A. So two single mutations, so two different mutants were created. And then also position 150V was mutated to 150A and 158V to 158A. So we had really 4 different mutants. This design and construct of these mutations took 4 to 6 weeks. So they were constructed by gene art and then transfected into a cell line, so a B cell cell line which lacked any HLA expression, and in that way a transient pool and also a stable pool were created. And then in flow cytometry, it was assessed whether there was binding of this monoclonal antibody to these different mutants, and of course also to the HLA-A1 wild type. So here's the first data that I want to show you. So this is data not of the monoclonal antibody of interest, but of actually a pan-HLA class 1 antibody. Because of course, when you introduce a mutation in the HLA molecule, you still want to confirm that there's not such a big conformational change that nothing is going to bind anymore. So here we see the data from both the transient and the stable pool. So we have first the 4 mutants, and then in red the wild type. In gray we see the negative control, which is the isotype control, and then the different colors are all the different mutants. And here you can clearly see that this pan-HLA class 1 antibody still binds to all the different HLA-A1 mutants. And then we tested the monoclonal antibody, so the A1 specific antibody. And what you can see here, so I've marked it with the red arrows, that there's no binding anymore when we mutate the position 44 to an R or an A, but there's still binding if positions 158 and 150 are mutated, and also the wild type still binds. So this really confirms that position 44 is really the crucial amino acid that really makes the binding of this specific monoclonal antibody to the HLA-A1 molecule happening. So therefore we conclude here that this residue 44K is the crucial amino acid for this monoclonal antibody, as we see that there is binding when we test the wild type. There's also binding when position 150 and 158 are mutated, but there's no binding if position 44 is mutated. So this was for us a very nice proof of principle that this strategy works for this HLA-A1 specific monoclonal antibody. And then we actually wanted to look further into HLA class 1 and specifically HLA-DQ. because HLA-DQ antibodies are very common after transplantation, so it's actually the most prevalent specificity after kidney transplantation. And the same study which I showed you before from Ruth Sapir-Bigatse from Canada showed that there is actually a residual effect on graft failure of unverified HLA-DQ eplets. So when we look at the total of HLA-DQ eplets, there are still some that are verified, but also some that are unverified. And she showed that there's actually still a residual effect of these not verified DQ eplets, which shows us that there's still a lot of relevant DQ eplets to be identified, and currently only 20% of the DQ eplets have been verified by a monoclonal antibody. So therefore, our lab has focused on the production of DQ-specific human monoclonal antibodies. And what we found actually is that when we analyze these reactivity patterns of these DQ antibodies, some really identified a single amino acid which we could correspond to a previously described eplet. But for some, we had the same problem of these reactivity patterns, so that we found multiple amino acids that are always present simultaneously on these alleles, and we cannot really investigate this further with the single antigen bead assay, or actually the alleles that are present in vivo, let's say. So therefore, I want to show you some data of these HLA-DQ experiments that have been performed. So this is a single antigen bead data of a monoclonal antibody that is specific for HLA-DQ3 and DQ4. So this antibody has been made from a producer that was a DQ6 and was immunized by DQ3. And what you can see here is we also did, so the BCM is the background corrected MFI in the single antigen bead assay. We also did some FOX test and a CDC. And what you can see here is that actually the combination of residue 52P and 53L, or the 140T, or the 182N, are actually uniquely shared for these DQ3, DQ4 alleles. And if we look at the HLA-DQ molecule, so here we see the DQ molecule from the side, you see that position 52 and 53 are together quite close to the peptide binding groove, and position 182 and 140 are weighed down more closely to the transmembrane region. So here we wanted to see which of these amino acids is now crucial for the antibody binding. And just to show you that indeed also here the producer alleles, the beads with the typing of the producer is indeed negative. So here again we can see that these residues cannot form an eplet together, and therefore there were constructs made with single amino acid mutations of position 53, so a mutation from an L to a Q, and also position 140 and 182. So again, 3 HLA-DQ3 mutants that were made. And here we go to the data. So here again, we first see the positive control. So here this is a PEN DQ antibody, just to show you that by these single amino acid mutations, there's no conformational change that results in the total Cs of binding. So here we can see that the PEN DQ antibody really binds nicely to both the wild type, here in red, and also the 3 different mutants. And then we go to the data of the monoclonal antibody, and here we can see that it also still binds. So the monoclonal antibody binds to the wild type, but also binds to these 3 mutants. So that was a bit disappointing, because we saw, okay, they're still binding to the 3 mutants. So apparently this single amino acid mutation on either location is not enough to abrogate the binding. So then we thought maybe position 55 plays a role in the binding. And position 55 is a position that is also included in other HLA-DQ aplets on different alleles. And it's very close to the position 52 and 53. So here the position 55 is in yellow. And you can also see here that the 55P is really unique for the DQ3 alleles, while also the DQ4 has and the DQ5, 6 have an R, and the DQ2 has an L. So the next step was actually to produce additional mutants where position 55 was mutated, but also a double mutation. So here in the second mutant, the position 53 and position 55 were both mutated. So this is the data of all these mutants combined, let's say. So I want to focus on these mutants, these highlighted mutants. So first, we already seen that position 140 and 182, if there is a single amino acid mutation, there is still binding here. So in gray here, we see again the negative control, and in the colors, all the different mutants. And then if we look at the double mutation, so the position 53 and 55, we see that there's no binding anymore. While actually, if we look at the position 55 mutation and the position 53 mutation, they're still binding. So in dark green, we have the double mutation, and then in light green and orange, you have the single mutations. So here we see that actually both these residues, the combination of these residues are crucial for the binding of this monoclonal antibody to HLA-DQP3-01. So that was very interesting to see. And well, we also had some other DQ antibodies that we would like to test. So here we have another DQ antibody which had this unresolved reactivity pattern. So here we can actually see, so this is a monoclonal antibody that is specific for not only DQ3, DQ4, but also DQ2. And all the residues that you see here, they're all uniquely shared by this combination of these alleles. They're all present only on the reactive alleles and absent on the negative alleles. So we have the position 53, where we already had a mutant, but also several other positions. So we decided first to focus on position 84 and 87, to also make some additional mutants. So here we made a mutation to position 84, so from a Q to an E. So again, from the residue of immunizing residue to the self residue of the producer, but also position 87, and again a double mutation where both 84 and 87 are mutated. So here again we see in gray negative control and in colors all the different mutants. So this is the binding profile of this other DQ3 specific antibody. And here we look at the positions 84, 87, and also the 53. So if we start down, we see that position 53, this mutation does not lead to any cease of binding, so there's still binding here. Also position 87 in purple, there's still binding. But if we look at position 84, we see that there's no binding anymore. And also in the double mutation 84 and 87, there's no binding anymore. So this really showed us that indeed residue 84Q is really crucial for binding of this monoclonal antibody to the DQ3 molecule. And then we also had another DQ3 specific map, which is has a bit more narrow pattern. So this is really only DQ3 specific. And here we thought that residue 55P is really the uniquely shared residue, which is a residue that corresponds to eplet 55PP in the epitope registry. So we thought that indeed this was the residue of interest and so the eplet. And yeah, since we had already the mutation on the position 55, we would like to confirm this with this study. So when we test this monoclonal antibody against different mutants, you can see that indeed when position 55 is mutated, so from a P to an R in light green here, there's no binding anymore. And yeah, of course, if there's a double binding where also position 53 is mutated, yeah, there's still no binding anymore because this 55 position, 55P is not present anymore. So this was a confirmation that what we thought, that residue 55P was indeed a crucial amino acid, that's also confirmed by this mutagenesis study. So these were all the monoclonals that were specific for at least the HLA-DQ3 allele that we had in our repertoire, let's say. But there was also another monoclonal antibody which is specific for HLA-DQ4, 5, and 6. And here we thought that residue 55R, which is also an eplet in the epitope registry, is really the one that's uniquely shared by these alleles and is the eplet for this monoclonal antibody. So here we see the position of 55 in yellow on the HLA-DQ6 molecule, so again seen from the top. And importantly, this monoclonal antibody should not bind to any DQ3 allele. As you can see already in the negative alleles in the single antigen bead assay, the DQ3 alleles are negative. But this is the position 55R that we are interested in. And of course, we already had this DQ3 mutant where we made the 55P to a 55R. So therefore, we thought, okay, maybe we can make a sort of gain-of-function mutation where we can make this antibody, which should not bind to DQ3, actually bind to DQ3 when this one crucial amino acid is mutated. So that's what we've done here. So here, it's important to tell you that the negative control, the monoclonal antibody that we use for the negative control, that's this DQ456 specific antibody. So here we can see that indeed in gray, this monoclonal antibody does not bind to the wild type here on the bottom, but also not to any of the mutants, except when position 55P is mutated in a 55R, and also again the double mutation with the position 53 and 55. So this is really interesting data, I think, that we see that a monoclonal antibody that's specific for DQ456, where we think that position 55R is really a crucial amino acid, that we can actually make it bind to a DQ3 molecule when only one position is mutated. So yeah, that's the data that I would like to I wanted to show you. So we really see that site-directed mutagenesis of these HLA molecules is a feasible method to resolve the reactivity patterns of HLA-specific maps. And that we can use it for HLA eplet verification. And yeah, it's a feasible method. It doesn't. It took within 2 months. Actually, we had data of this first HLA A1 specific monoclonal antibody. So that's very fast. And it really demonstrates, especially this last example, that a single amino acid can be crucial for the binding of a specific map to its target antigen. And yeah, of course, we will continue with this research, and we will focus mainly on more unresolved HLA-DQ and also HLA-DR reactivity patterns of the monoclonal antibodies that we still have in our lab. And we also would like to use this method further to study other factors influencing, for instance, antibody affinity by maybe mutating amino acids that are part more of the structural epitope, so the surrounding antibodies surrounding the functional epitope of our eplet. So yeah, with that, I really want to like to thank you for your attention, and of course the team from the transplantation immunology in Leiden, so Cynthia Kramer, Frans, Klaas, and Sebastian Heid, and of course the team from One Lambda, so especially Dave, Tina Meng, and Ujwala for the great work that we've done together, and yeah, hopefully more to come. Thank you.
If I didn't say, we're going to hold all the questions till we have the round table at the end. So our next speaker also needs no introduction, Dr. Marcelo Fernandez-Vina. He's professor in the Department of Pathology at Stanford, and he's director of the HLA laboratory there. He's also been involved in just about anything and everything involved in HLA in our community, in the world, in the government, in ASHI. He's one of the few people in the room who's been in HLA much longer than I have. Oh, wait a minute, Howie Gable's over here. He's much older than everybody in the room. So, except for Howie, Marcelo's been around for a long time. So, without further ado, Marcelo.
Thank you. Thank you. And how do I point? We just here, no? Okay, I'm going to use that one. So, yes, I wanted to, and this was a great presentation, Susanna, and actually very reassuring, I'll comment. And what we proposed is the definition of of serological alleles, do an update, taking into account structural features like the ones that Suzanne just described, and we call them these residues that determine epitopes. And indeed, we use those residues for for the definition of the serotypes that we proposed that would need to be updated. So I'd like to acknowledge Kazu Osogawa, who did most of the work at the computational level, and we discussed this over a long time, the different residues that we would be adding, and we did a couple of weeks ago a webinar. Just a couple of things about the HLA workshops, the International Histocompatibility and now Immunogenetics workshops. It is a reservoir of common knowledge. It has served as a standardization and provided specifications for naming and tracking features of HLA alleles. And for several workshops until the 13th, there were workshops where serology was done, and after that, it practically stopped. I would like to go to the manuscript from by Rod and Van Leuven. This is 1962, if I'm not wrong, where they defined, for example, a way they did cluster analysis, and they defined for A for B as a diallelic system, and actually that's our current BW4, BW6. And you know, many years later, at those times, they didn't have sequences as references. But they were able to do epitope mapping, and they named them based on the distribution. Many years later, we came to see, for example, that residues 82, 83 define BW4, BW6. And interestingly enough, for example, when we ran the 13th workshop, we saw some monoclonal antibodies that missed, for example, B46 and B73. And indeed, these antigens were listed as being BW6 positive, but indeed they were not. And actually, to add to the epitope of BW6, we would like to put glutamic acid 76. And with this, we would have some alleles that may be negative for either BW4 or BW6. We know that many epitopes were mapped over time, and that was an HLA antigen that is bearing many different epitopes that can distinguish them. The studies included human sera at the time, then monoclonal antibodies, and the definition of many of the serologic specificity was based on the quality of the reagents and abundance of the reagents. Many splits were defined but never named because there were not enough reagents. And so that is a gap that we have today. If you look at this HLA nomenclature in 1987, this is a summary, and indeed you will notice that there are a few things more there that we have in the HLA nomenclature that were probably added in no later than 1995. I would comment only, for example, in this workshop in 1984, looking at HLA-D typing, they split 3 HLA-DR4 alleles. So we knew that the splits existed, and they were never named. And that's really bad. That was done based on mixed lymphocyte cultures and D-typing, and we know now the sequences. But indeed, that is the definition of these splits is lacking, and you see these splits all the time when you do an anti-HLA antibody testing. Indeed, there were many splits that were noted through the workshops that they had not been named. And after that, after 1995, that was the last nomenclature update. You can see the new associated antigens that were assigned, but you see some A2 associated antigens, but A201, for example, doesn't have an associated antigen. And so, indeed, there is a lack also of defining associated antigens. And we knew that the HLA nomenclature using the Fairfield, as has been suggested, has gaps. For example, in the 13th workshop, we saw a very distinct pattern for B5001, B5002. This is inclusion reactions of sets of monoclonal antibodies that we did, and you can see B5002, as it has been described, has the same pattern as B45 on top. but also see a novel allele at the time, that is today B4504, looks like B50. So indeed, the name doesn't take into account the serologic definition. And we use solid phase assays that contain a set of antigen preparations to define the assay in many aspects. We do an in silico, or we call virtual cross-match, and now what? A risk assessment. We use the assay to do that, but sometimes the panels are not complete. And the idea would be if we could actually use panels that are more extensive based on common alleles. So it has been suggested, well, we do 30,000 single antigen preparations to cover all the alleles that have been described. And that is not possible. And at base, we see that the most common alleles are represented in the current antigen preparations, but some ethnic specific alleles are not represented, and actually they are common. There are some serotypes that in my eyes are overrepresented in the single antigen bits because there are alleles that are exactly the same by serology. And so we need to develop a comprehensive, intelligently designed panel to evaluate the assays. We came together with several colleagues, very esteemed and well-recognized colleagues, and put together the system that we had initially thought with CASU, but we went over extensive discussions, and you can see, recognize the names, including Steve, Marsh, Rhonda, Holsworth, Sebastian, Gottfried Fischer, Kathy Murphy, Martin Myers, and myself. So we agreed that we perhaps could consider structural features to classify HLA alleles into serological specificities. We developed a computational tools, and indeed there were some currently conversion tools, that one of them is Alan, that, for example, lacks the recognition. For example, for B1403, does not call B65, calls B14. And you know, if you have a donor that this B14 is not mapped in UNOS to anything, the only one would be donors that are broadly typed as B14. And so we thought that perhaps there was a need to develop this. And what we did, we went back to literature and looked at monoclonal antibodies that were published since 1985. And we have in the manuscript a number of references and methods on how we identified residues that we use to map the residues that define epitopes. And this could be used in combination to define WHO-accepted antigens, and actually wrote a program for that. In this report, we also put BW4, BW6, BW46 negative, and we put HLA-C, that indeed we know that there are epitopes that correlate well with KIR-C1 and KIR-C2, with B73 and B46 falling in that group as well. And this is a proposal there. For example, here you can see some key residues, 62G, that is a well-recognized A2, B17 epitope. You see A2, A9, A28, residue 127, and so on. We followed some of these residues to identify, to put them in the identification of antigens. And for example, even if sometimes we didn't have monoclonal antibodies, we knew that the typical A2301, A2402, that are clearly distinguished by serology, differ by a couple of amino acid residues. Therefore, those residues are important to be mapping, to assign serotypes as well. Indeed, we came up with sets of residues for HLA-A that, for example, we have 25 residues that we can include to define all the serotypes that were defined to present. And you see, for example, the ones that define A2 and the associated antigens, they are in gray and yellow. But you see other residues that, for example, correspond to other serotypes. For example, the A23 and A24, you have to put residues 166, 167 at the end. Indeed, by looking at the common serotypes, and they are prototypes at the molecular level, defined at the molecular level, we found these residues and these positions, and basically we could start defining them. And with this work, I would say when we found an allele that has no mismatch at all residues with the prototype, let's say A0201, we would call it a full serotype. We would call a serotype only alleles that match at the key residues, but not at all the residues, and those can bear other epitopes shared with other HLA antigens. And finally, we defined incomplete those that have one amino acid mismatch in either of the colors, at least two, to assign something in the name that those are incomplete. And actually there are many, and as you're going to see, the incomplete antigens are all rare alleles. Here you have, for example, we propose to start naming serotypes A0201, A0202. For example, A0202, A0205, they are in black, and arginine at residue 43, and many of you guys see A0202 specific antibodies or vice versa, A0201 specific antibodies that don't react with A0202, and A0205 in general come together. And so here you have a number of residues, and doing the work we found, for example, some alleles, for example, A0219, we described it in Argentina, very common in native populations, in some native populations, and it's a hybrid of A2 and A24. So indeed, we needed to create a common serotype specific for that too, using the residues that are shared with A2 and A24. So indeed, this is the kind of work that we put in there for defining serotypes. And for example, what we did after we came with this validation, with this set of serotypes, we used the pre-existing dictionaries, and we saw that we were defining, for example, B409 as B45, B4406 as B47, and so on, B5002, as I mentioned to you, as B45. So indeed, we did a validation based on pre-existing data, and Alan doesn't cover, for example, some of these serotypes as the split level, but you can see, for example, the two B14s that would come as B14 as being 65 based on the residues that we selected for defining those as well. And so indeed, this is adding more resolution to some serotypes that were not assigned, because sometimes there was incomplete serology when these alleles were submitted to the IMGT. For example, here we have an interesting one, B1515. It's a matter of debate even in my lab, but I can tell you guys that B75, and today Ketty confirmed to me, Ketty, are you here? Raise your hand. That B1515 comes as B75 more common than B62. For example, B4802 is B72. Here we have the B15 and the B70 splits, and there are key residues to define B15 and B70 that we have used. They are all in the manuscript, and you can see that the residue, residue 63, let me go back for a second. Am I good here? Residue 63 can distinguish some of the subtypes of B75 from B63. Let me show you a little bit more on that. Here, for example, have some cases there, and actually it fell B15 falls as B75. And for example, B4802, if you compare the alignment, really shares the same residues as B1503, that is B72. Kathy Murphy provided us with a couple of Xera on the left, one that reacts with B4801, and another one that on the right that reacts with B72, and actually B4802 comes with the same reactivity as B72. So indeed, this is to cover some of these limitations. And also what we did is we tried to be systematic in naming subtypes. For example, we knew, and we can distinguish A2403 from A2402, the proposed there. But there is an allele of A2304 that differs exactly by the same substitutions from A2301 at residues 166 and 167. So we feel that there is a need to define that serotype as well, just to be comprehensive and really use and systematic. For example, we know BW4, BW6, the related, the B16, the B12, the B25, the B21 and B27, that if you follow BW4, BW6, you get the split or the associated antigens. But for example, we have B1524, that is like B62, B1501, but differs in BW4, and we would like to name that allele, that as an associated antigen. The same thing goes to B0802, that differs from the common B0801 by BW4, BW6. This is a B8 that is BW4. So we believe that this needs to be recognized formally. And you know, it's not only the BW4, BW6 epitope, but actually the same positions define other epitopes. That's why we call them residues that define epitopes as well. So I mentioned to you then that there are B62 associated antigens that now we're going to call, that is BW4, that is B1524. We have a B71 that is BW4 as well, that is B1523. And we go by the most common allele to give the name that we propose there. You can see a dash because Steve would not allow us to put the B and the number because it looks like a formally recognized antigen, but the idea is that we would like to propose it to the nomenclature. Here you see the DR4 subtypes. We use residue 71, for example, to define some of the subtypes. We put DR1410, that is a hybrid and looks like DR4 by serology, but differs, for example, at residue 60 from the other DR4s, and shares sequences with 1454, DR1410. So DR1410 would map to DR4. And one of the things, and we can comment, is, for example, residue 71, we use an arginine or a lysine, are a couple of residues that have the same charge that actually could be equivalent. So indeed, DR401 includes DRB10401 and DRB10404 because it's an alternative residue that where in that position the same charge plays a role. And you will see that we use that in other positions, in 71 as well. And looking at 71, you can see that we can split DR51 into 5101 and 5102, but indeed DRB50103 differs there as well and is common, so we propose to create a serotype for the DR51 for this allele as well. And you can see, for example, the DR52 into 5201 to 5202 that you often see with your sera that actually using residue 60 that comes better to distinguish these two splits of DR52. We didn't go much in detail for DQ as currently defined because we think there is more work and would like to see the splits. But you can see, and I am very happy to see, for example, 84 to 90, we used to define DQ1 from non-DQ1, and actually Suzanne mentioned residue 84. We couldn't break them out there, but you know, we used the whole set, and this is the DQ2, the non-DQ1 antigens. And definitely this we could discuss. We think the residue 45 is the one that defines DQ7 as it was described originally by TA10. It's a monoclonal antibody, probably 1985. So that seems to be a residue that we would like to consider for the definition of DQ7. We also use residues to define DQ alpha because there is no formal nomenclature. You are going to see that we propose to call DQA and follow with the first field and use, this looks familiar to you. We are using those names anyway today, but we would like those to become formal nomenclature. And there has been a lot of data showing that there are antigens defined by both subunits. And actually we proposed, for example, to name formally combinations in cis that we know define some, that react with some of our sera. For example, DQ alpha 05 paired with DQ7, we'd like to give a name. And we chose the pairs that are where in the haplotypes are in cis, because we're going to be seeing always, because they travel together. So for DQA1, DPA1, and DPB1 antigens, we also came with serotypes for that, and you can look at them in the paper, but we define DQA1, DPA01 and DPA02. O1 includes O3s, and O2 includes O4s, and you probably see those in your test as well. We use the common and well-documented alleles to assign serotypes. We didn't want to leave uncovered common alleles with full or at least serotype forms. And so we have data for some well-documented alleles that actually their serotype corresponds to a common allele, and indeed you are going to see that they are shown there as well. And here is the number of residues that we use to define the positions critical for each of the loci. DRB1 and uses 13, DQB1 uses 13. They are not necessarily the same. And you can see the currently assigned number of antigens assigned, and you see the numbers that we proposed. It looks big, but on the other hand, it's only 81 Bs that we propose, 53 As, and so on. So this is the number, the percentages of full serotypes or full or serotypes that we assigned for all the alleles that we use in the version, for all proteins. And you can see here that all common alleles either have a full serotype or a serotype assignment. That indeed, when we do antibody screening, 99.5% of our donors are going to have one of those. And if we design a panel intelligently to cover that, we're going to have a good DSA assessment, or if we have a better representation in our panel. And you see that the well-documented are less covered. We have some incomplete, and the same thing is for rare alleles as well, that in yellow and gray. So we found in our data set 498 proteins, or 452 proteins, where the first field does not coincide with the serotype that we proposed there. And indeed, this fixes a gap, as like the one I mentioned for B4802 as well. We developed criteria for identifying amino acid residues that determine serologic epitopes. We developed a logic for serotype assignment. This can be done by computer. We identify alleles with serotypes that currently do not have an official WHO designation. And the methods can be implemented to systematically assign serotypes for all HLA alleles, indeed, the ones that come in the future. And so this could be run with new versions of the updates on the databases. 92.2% of all alleles were assigned as full or serotypes. 99.77 have a serotype or a short. 100% of the common alleles, as I mentioned to you, are full, 84%, and 16% are serotypes. And so there is more work to do, for sure, in this, and identify more residues, or perhaps create other serotypes. And as I mentioned, almost 3% of the alleles contain the first field designation that does not coincide with the serotype. And what we wrote in the manuscript, we would like to propose to the WHO Nomenclature Committee for factors of the HLA system that these newly defined serotypes become officially accepted, having new antigen or associated antigen status. So therefore, we don't diverge by calling things locally in our lab, which then does not allow us for communications and so on. That has been the standard of nomenclature. So this is the proposal we have for, and Steve will put this to consideration to the committee. But the idea is that once this becomes official, then accrediting agencies can pick up on this and then put them in the standards, and then they would go to even some of the organ allocation agencies and so on. So anyway, this is it, and of course we can discuss.
Thank you, Marcelo. Now I have a couple slides. Just one comment for Marcelo. You said it in the talk. I think you coined a new term for us, RDEs, residue-defined epitopes.
Yes.
Call them RDEs. That's, yeah,
Because
I know.
not eplets are perfect.
I'm not talking about, no, because you're defining it by the serology, so it's a residue-defined epitope. All right, can I have my slides? Who's doing the slideshow? Oh, gotcha. Okay, so what defines an epitope? I just wanted to show a couple examples here real quick. We've seen several of these in our laboratory. So here's the first case. This person presented about 56 days post a kidney transplant and presented with a rising creatinine and a biopsy-proven AMR, and we ran the single antigen beads, and they really didn't show anything. However, at our lab, we always run two methodologies, and we ran the flow PRA beads, and they look like this. And we occasionally see these disconnects, which is why we, and I'm sure everybody here, runs multiple different testing programs and platforms to pick these things out. We ran the flow specificity beads on this one, and it confirmed that it was a DSA, a DRB50101. And if we go back and look here, I don't know if I have a pointer, right here, DRB50101 was one of the very first beads here in there, although no one would call that positive by any stretch of the imagination. And clearly a disconnect with the flow PRA. DRB50101. And I called Jarhow, who was very interested in this. And anyway, this one case led to the development of the I beads. And on this one here, we see on the left, we have the standard bead panel. On the right, we have the I bead panel. And you see the DRB501 is negative on the standard. It's positive on the I bead panel. And the only difference in that DRB50101, it's the same construct, has different peptides. Has different peptides loaded in the groove. So we believe that on occasion, you can actually have an epitope which is peptide dependent, depending on how you're looking at it. And also to follow up on that, there was a recent publication from Dr. Zeevy's lab looking at, and the title was a positive flow cross match with discrepant testing following COVID vaccination. So this is a regraft waiting for a second transplant, was going to be transplanted across a mismatched DR7 from the first transplant. But prior to the COVID vaccination, there was no DR7 antibody. Subsequent to the COVID vaccination, the two upper one is pre or the specificity beads. It doesn't show DR7. The single antigen beads were negative for DR7. On the bottom panel C there now is post-COVID vaccination where the specificity beads are positive and you can deduce a very nice DR7 antibody specificity out of that. And then here are the beads pre and post, and anyway, the bottom line of these two is that even with or without EDTA, there was no DR7 detected on the single antigen beads, but the DR7 was detected on the flow specificity, or the Luminex specificity beads. Again, another case demonstrating the possibility that the peptides in the groove can determine how the antibody sees that epitope as well. So I think this is something we have to be aware of, and I think everybody in this room does it, run multiple types of platforms, different constructs. Flow PRA beads are a different antigenic construct than the single antigen beads. And it's important that we do that so A, we don't miss things, and B, we can understand some real biology that's going on with this. So I will stop. That was the end of my presentation. Now we're going to invite everybody up for a round table. And